Modern chemical engineering evokes images of sterile steel reactors and precise digital gauges. But if you strip away the stainless steel, the underlying thermodynamics match the soot-stained terracotta smelting furnaces used 3,000 years ago. This connection is explicitly recognized in contemporary academia. Look at this syllabus for industrial chemistry. Under the core module for metallurgy, there is a dedicated section on ancient Indian metallurgy, sitting directly adjacent to modern physical chemistry modules like evaporation, filtration, and distillation. Grouping these subjects together recognizes that the same unit operations governing modern chemical plants were operational in ancient furnaces. Viewing ancient history through the strict framework of industrial unit operations reveals a highly advanced material science that predates the European scientific method by millennia. Between 1300 BC and 1600 AD, Indian scholars codified an empirical discipline known as Rasashastra, literally translating to the science of liquids. Unlike the mystical pursuits of Western alchemy, Rasashastra was grounded in rigorous, reproducible material categorization. It was an applied physical chemistry. These practitioners successfully engineered solutions to complex thermodynamic bottlenecks and synthesized bioassimilable nanoparticles centuries before John Dalton proposed the modern atomic theory. To prove this, we will examine their chemical taxonomy, the extraction of highly volatile metals, and their proto-nanoscale surface chemistry. What emerges is a codified, highly empirical methodology for early industrial manufacturing. Around 500 BC, the philosopher Maharshi Kanad proposed that all matter could be divided until reaching an indivisible unit, a particle he called the parmanu. This presents an immediate chemical problem. Without tools like mass spectroscopy or Dalton's atomic weights, how do you accurately categorize and utilize these invisible particles? The text Rasa Ratna Samuchaya solved this by classifying matter based on functional reactivity. The first category is the Maharasas, or primary minerals. These were grouped specifically for their proven ability to bind with and amalgamate liquid mercury. Next are the Uparasas, the secondary minerals. These include elements like sulfur, classified together because they act as necessary catalysts and reactants to drive chemical changes in heavier ores. Finally, the dhatus represent the pure metals, the stable base elemental products yielded at the end of these reactions. By organizing the physical world around what substances actually do rather than what they weigh, ancient chemists built a predictive model for complex molecular interactions using only observable behaviors. This theoretical framework was applied at an industrial scale. At the Zawar mines in Rajasthan, archaeometallurgists discovered the remnants of a massive engineering operation. Smelting copper is a straightforward process of applying high heat to melt the ore. Zinc, however, presents a severe thermodynamic hurdle. This chart shows the phase changes of the two metals. Zinc vaporizes into a gas at approximately 907 degrees Celsius. Crucially, the temperature required to extract it from its ore is actually higher than its boiling point. If you heat zinc ore in a standard open furnace, you do not get a pool of liquid metal. The zinc simply oxidizes or escapes into the atmosphere as a useless vapor. To capture this elusive gas, the Rajavadins invented a precise piece of equipment, the Tiryak Padana yantra. In the upper chamber, intense heat is applied to a sealed terracotta retort. The zinc ore reaches its extraction temperature and immediately sublimates into a vapor. Because the system is sealed, the expanding pressure forces the turbulent gas downward, driving it through a narrow neck into a lower, isolated chamber. Here, an extreme temperature drop forces the vapor to condense. The thermal shock causes the gas to instantly crystallize into pure metallic zinc. The physical evidence of this extraction method survives in artifacts like beadryware, a high zinc brass alloy requiring immense quantities of pure metal to produce. The Tiryak Padana yantra was a specialized instrument engineered to trap a metal that naturally dictates its own escape. This mastery of phase changes extended beyond metallurgy and into highly specialized pharmacological chemistry. Ancient medical practitioners wanted to utilize the properties of heavy metals, but faced a strict biological barrier. In their bulk form, heavy metals are highly toxic and utterly unusable by human cells. Their historical solution was a precise chemical detoxification process known as shodana. The base metal is subjected to exhaustive mechanical grinding, a process of extreme trituration, alongside specific uparasas, most importantly, raw sulfur. By reducing the material to the nanoscale, the ratio of surface area to volume increases exponentially, altering how the substance interacts with its environment. This state change effectively neutralizes the bulk toxicity. The heavy metal payload becomes bioassimilable, allowing it to interact safely and efficiently with human cellular structures. Through shodana, ancient chemists engineered precise surface chemistry to manipulate human biology, long before the invention of the electron microscope confirmed their results. The dense, archaic Sanskrit terminology found in these texts often obscures the rigorous empirical science operating beneath the surface. But when we translate the syntax, the parallels are exact. The Puta calcination cycles are early, systematic applications of thermal decomposition. The Tiryak Patana yantra is a mechanical execution of fractional downward distillation, and the production of basma mirrors the modern science of bio-nanoparticle synthesis. Evaluating these historical texts through the vocabulary of physicochemistry is essential for recovering proven industrial techniques that have been lost to time. Which brings us back to the modern university syllabus for industrial chemistry. Ancient Indian metallurgy is taught alongside modern fossil fuels and boilers because the mathematics of unit operations have not changed in 3,000 years. Whether manipulating the extreme thermodynamic phase changes of zinc or re-engineering the biological payloads of heavy metals, the logic remains a constant, unbroken pipeline. The Rasavadins of ancient India were the original architects of industrial material science. As we push the boundaries of modern chemical engineering, the next major breakthrough might require us to look backward and recover the remaining technical protocols of the ancient